Hello dear students, we are back again with another video lesson. In a previous lesson, we finished section 2 in chapter 4 about the sound intensity, relative intensity and resonance. Today's lesson, we are going to talk about the harmonics. In section 3, chapter 4, we will talk about the harmonics. So at the end of the lesson, you will be able to understand and learn what is the harmonics and what is the type of the harmonics. Standing waves on a vibrating string, we have three different types of harmonic: on a string, on a closed pipe at one end, and open pipe at both ends, and closed pipe at one end. At first, we will talk about the standing wave on a vibrating string. Okay, in a vibrating harmonic is in a vibrating string. For example, a variety of standing waves can occur when a string is fixed at both ends. So what is the conditions of the standing wave and harmonics? Like, for example, if you have a string, the string must be fixed at both ends, okay? And fixed at both ends and set into vibration. The vibrations on a string, consist of what? Many standing waves together at the same time, so each of which has different wavelength and frequencies. In the vibrating string, harmonics in a vibrating string, we have many different types of harmonics. Each harmonic has its own wavelength and frequency. We will talk and explain one by one in detail. What is harmonics, guys? Harmonics are integral multiples of the fundamental frequency. Each harmonic is related with the fundamental frequency. What is harmonic series? A harmonic series is a series of frequencies. We have many frequencies. A series of what? Frequencies that includes what? Fundamental frequency. That includes what? Fundamental frequency. F1. Fundamental frequency, its symbol is F1. What do you mean by F1? Fundamental frequency, or the simplest harmonic in the string. And integral multiples of the fundamental frequency. F1 is what? Is fundamental frequency, okay? Fundamental frequency. F1, the first harmonic, which is fundamental frequency related with the other harmonics. For example, how can you find the second harmonic? Frequency in the second harmonic is equal to 2 times F1. F3, 3 times F1. Fourth harmonic, 4 times F1. So, what is the definition of harmonic series? Okay, harmonic series is equal to what? Is equal to a series of frequencies, including what? All frequencies including what? Fundamental frequencies. And integral multiples by what? The integer or integral number by the fundamental frequency. What is the fundamental frequency? F1. Fundamental frequency is the lowest frequency. Is what? Is the lowest frequency of vibration of standing waves. Okay, in all types, guys. Once again, listen carefully. What is fundamental frequency? Is the lowest frequency in the standing wave, or the lowest frequency of vibration of a standing wave. Question 22 in chapter review. What is the fundamental frequency? How are harmonics related to what? To the fundamental frequency. Question 22 in chapter review. What is the fundamental frequency? Fundamental frequency, as I told you, the lowest possible frequency of vibrating system. How are harmonics, like second harmonic, third harmonic, fourth harmonic, related with the fundamental frequency? The harmonics, F1, F2, F3, F4, are integral multiples. What do you mean by integral multiples? 2, 3, 4, 5, 6, and so on. Okay? Multiple by what? Of the fundamental frequency. For example, F2 is equal to what? 2F1. F3, 3F1. F4, fourth harmonics, 4F1. So, in this relation, we can achieve this relation. Fn, the frequency of each harmonic except fundamental frequency, is equal to what? Number of harmonics, 1, 2, 3, 4, except 1, because 1 is a fundamental frequency. N times what? N times fundamental frequency. What do you mean by F1? Fundamental frequency. N, number of harmonics. Fn, frequency of each harmonics. Fundamental frequency, F1 has the lowest possible frequency. That is why we call it fundamental or basic frequency. Has the lowest possible frequency because frequency is inversely proportional to the wavelength. Guys, if the fundamental frequency has the lowest frequency, it means that the wavelength has the longest wavelength in the fundamental frequency. In the fundamental frequency, F1, we have the greatest or largest possible wavelength, and it has the lowest number of antinode in a vibrating system and equal to 1 antinode. Okay? Harmonics in a vibrating string. Harmonics in a vibrating string or rope. In a standing wave on a vibrating string, or harmonic is in a vibrating string. In a string, the ends of the string which cannot vibrate must always be nodes. The two ends must be what? Node. Okay, now I'm going to tell you what is node and what is the antinode. Okay, what is this figure? This is string. Okay, after vibrating the string, we can produce 1 antinode and 2 nodes. The two ends that are fixed at both ends, the two fixed ends is called what? Node. Node and node. In a vibrating string, harmonics or standing wave in a vibrating string, the first harmonic number 1, how many nodes do we have? We have 2 nodes. So the maximum point is called antinode. Maximum point is what? Antinode. How many antinodes do we have? We have 2 antinodes. Okay? The ends of the string which cannot vibrate must always be node. And the center of the string experiences what? The most displacement, and so it is an antinode. First harmonic in a vibrating string, guys. First harmonic. First harmonic, it means that n is equal to 1. How many antinodes do we have? In this case, this string vibrates with 1 antinode and 2 nodes. In a vibrating string, the two ends always node? Yes. The two ends of the string is always must be node to produce the standing wave in string. How many nodes do we have? As you can see, we have 2 nodes. What is the difference between small n and capital N? Small n is number of harmonic. What is small n? Number of harmonic. What is n? Node. N is what? Node. A is antinode. A is antinode, N capital is node. How many nodes do we have? 2. How many antinodes do we have? We have 1 antinode. In a vibrating string, number of nodes is equal to number of harmonics always. N is equal to antinode always. This is very important, guys. This is first harmonic in a vibrating string. First harmonic in vibrating string consists of how many antinodes? Consists of 1 antinode. And how many nodes? 2 nodes. This is the simplest harmonic, the simplest standing wave in a string produces by the string. This is antinode, the maximum point displacement, and the 2 ends is node. Guys, look. How many wavelengths do we have in the simplest standing wave in a vibrating string? Fundamental frequency has a half wavelength. Okay, how many wavelengths do you have? So you can make into 2 parts. Okay, we have 2 amplitude here, okay, as we studied in the section 3 in chapter 3, the amplitude, okay, is so in this circle we have half wavelength. From this point to this point, how many wavelengths do we have? We have half wavelength. Half wavelength is equal to what? Half wavelength, in this case, in the simplest standing wave, is equal to what? The length of the string. If you rearrange this equation, wavelength is equal to what? Is equal to 2L. So can we say when wavelength is equal to 2L, this is longest wavelength? Yes. Longest or greatest wavelength. When does the longest wavelength is formed in a vibrating string, standing wave in a vibrating string? When the string vibrates with one antinode and two nodes. Okay? One antinode and two nodes. This is the wavelength. Frequency is equal to what in the fundamental frequency standing wave in the first harmonic? Frequency, according to this relation, frequency is equal to what? Is equal to V over wavelength. V over speed of the wave divided by wavelength. So wavelength is equal to what? Is equal to 2L. Okay? Harmonics, this is first harmonic, n is equal to 1. Okay? F1, fundamental frequency in a vibrating string for the first harmonic is equal to V over 2L. So we have equation to find a number of harmonics, the frequency of each harmonics. Frequency of each harmonics is equal to NV over 2L. Okay? How did we get this equation? F1 is equal to V over 2L. For the first harmonic, guys, number of harmonic is equal to what? Is equal to 1. Replace into this equation. Instead of this n, write down 1. Number of harmonic, 1. 1 times Vv over what? Over 2L. In this equation, you can find frequency for each harmonics. Look at this relation. Fn is equal to Nv over 2L. This equation can be used to find what? Frequency of each harmonics. N is equal to 1, frequency becomes V over 2L. But if n is equal to 2, frequency is for the second harmonic is equal to 2 times V over 2L. Now I'm going to explain, okay? Guys, for the first harmonic, n is equal to what? 1. In the first harmonic or fundamental frequency for the vibrating string, how many antinodes do we have? We have only one antinode. How many nodes do we have? We have 2 nodes. Wavelength is equal to what? According to this relation, wavelength is equal to 2L over N. Number of harmonic is equal to what in the fundamental frequency? Number of harmonic is equal to 1. To find wavelength in the fundamental frequency, where in the first harmonic, 2L over 1 is equal to 2L. Look. In these two equations, you can find wavelength of each harmonic, 2L over N, frequency of each harmonic, NV over 2L. In these two relations, you can find wavelength and frequency of each harmonics. In the first harmonic, first harmonic in a vibrating string. First harmonic, n is equal to what? 1. First harmonic. In the first harmonic fundamental frequency, the string vibrates with how many antinodes? 1 antinode. How many nodes? 2 nodes. Can you draw the figure? Yes. The figure for the first harmonic, it will be like 2 nodes, 1 antinode. Look, how can you determine frequency and wavelength for the first harmonic in a vibrating string? As I told you, according to this relation, wavelength for each harmonic is equal to 2L over N. Frequency for each harmonic is equal to NV over 2L. Wavelength for the first harmonic is equal to what? Wavelength is equal to 2L over N. But for the first harmonic, N is equal to what? 1. 2L over what? Over 1. Wavelength for the first harmonic is equal to 2L. Yes, wavelength for the first harmonic in a vibrating string is equal to 2L. This 2L, can we say this is the longest wavelength? Yes. Longest wavelength. And shortest frequency or lowest frequency. You can say it's better to say lowest frequency, guys. Lowest frequency. So can we say fundamental frequency is equal to the lowest frequency? Yes. F1 is equal to the lowest frequency. What about if the question asks us to find the longest wavelength? What do you mean by longest wavelength? It means that the wavelength of the fundamental frequency. Wavelength number 1. Lambda 1. What do you mean by lambda 1? Longest wavelength. Lambda 1 is what? Longest wavelength. What about lowest frequency? F1. To find frequency, use this relation. To find frequency, frequency equal to what? Frequency is equal to what? NV2L. This is the equation. Replace. Frequency in the first harmonic, F1, is equal to 1 times V over what? Over 2L. What is this? This is the equation of fundamental frequency in a vibrating string in a standing wave. And also you can say this is the lowest frequency. What is this? Lowest frequency. Okay? Or greatest wavelength or lowest frequency. This is first harmonic, guys. Second harmonic, don't forget these two equations. Lambda n, 2L over n, Fn, and V over 2L. In the second harmonic, in a vibrating string, second harmonic, N is equal to what? N is equal to 2. And in the second harmonic, we have 2 antinodes and 3 nodes. In a vibrating string, in a standing wave, number of nodes always, guys, look, number of nodes always equal to A plus 1. And number of harmonics always equal to number of antinodes. How many antinodes do we have? 2. Can we say this is second harmonic, N is equal to 2? Yes. In a vibrating string, which of the following determines the number of harmonic? Number of antinodes. Number of antinodes determines the number of harmonic in a standing wave for string. The figure, it will be like this. This is string, okay? Guys, look, how many antinodes do we have? 2. We have 2 antinodes. In a vibrating string, number of nodes is bigger than number of antinodes by factor of 1. We have 2 antinodes. What about node? Node is equal to A plus 1, yes. 2 plus 1, 3. How many nodes do we have? 3. 1, 2, 3. 3 nodes. How can we determine the wavelength in the second harmonics? Wavelength in the second harmonic equal to what? 2L over N. Wavelength in the second harmonic, lambda 2, is equal to what? 2L over 2. This 2 will be cancelled. Lambda 2 is equal to what? Is equal to L. Can we say this is the longest wavelength? No. Longest wavelength, it means that lambda 1, not lambda 2. But guys, let me ask you a question. In a vibrating string, it must be indicated in the question, string or pipe. In a vibrating string, for the standing wave, harmonic, in a string, vibrating string, when does the wavelength is equal to the length of the string. What do you mean by this L? Length of string. What is L? Length of string. In a vibrating string, when does lambda is equal to L? In the second harmonic. In which harmonic's wavelength is equal to the length of the string? In the second harmonic, when n small is equal to 2. Or you can say when the string vibrates with 2 antinodes and 3 nodes. Vibrate with how many antinodes? 2 antinodes and 3 nodes. When this vibrating string vibrates with 2 antinodes and 3 nodes, which harmonics present in the string? Harmonic, the second harmonic. Harmonic number 2, second harmonic. Why? Because in the second harmonic, the string vibrates with 2 antinodes and 3 nodes. Guys, what about frequency? Frequency is equal to what? For each harmonic, NV over 2L. Number of harmonic 2. 2V over 2L. Okay? This 2 cancel with this 2. F2 is equal to what? F2 is equal to V over L. In another way, guys, look. Look, guys, for the second harmonic, F2, is it possible to say F2 is equal to N, F2 is equal to 2F1? Why not? Yes, you can do it. You can find the second harmonic if the first harmonic is given in the question. If I give you the first harmonic, fundamental frequency, can you find the second harmonic? Yes. How? According to this relation. F2 equal to 2F1, yes. How? Look, now I'm going to prove for you. In the second harmonic, Fn is equal to Nv over 2L. F2 is equal to what? Number of harmonic, V over 2L. If I take out this V over 2L to the other side, look. Guys, do you remember that F1 is equal to V over 2L? We studied this. F1 is equal to what? V over 2L. What is F1? Fundamental frequency. Fundamental frequency. And instead of this V over 2L, guys, look, rearrange. Take out this 2, multiplied by what? What is remain? V over 2L. V over 2L. And instead of V over 2L, can we write down F1? Yes, of course. Why not? F2 is equal to what? Bring down this 2. And instead of this V over 2L, write down what? F1. So this is harmonics is equal to the integral multiples of the fundamental frequency. Okay? The third harmonics, guys, in the third harmonic, number of harmonic 3. In a vibrating string, number of harmonic is equal to number of antinode. If number of harmonic is 3, third harmonic, it means that antinode also 3. Number of nodes in vibrating string is bigger than number of antinode by factor 1. If we have 3 antinodes, it means that we have 4 nodes. Okay? Draw the figure. 3, 1, 2, 3. 3 antinodes and 4 nodes. This is antinode. 3 antinodes and 4 nodes. 1, 2, 3, and 4. Okay? How can you determine wavelength and frequency of the third harmonics? For the third harmonics, wavelength is equal to 2L over N. Third harmonic, lambda 3, 2L over 3. So when does wavelength is equal to 2/3 of it is L? So can you write down this? Yes, like this, guys. 2 over 3 L. So what about L? Rearrange. You have to flip this. 3 over 2 wavelength. Okay. So when does wavelength is equal to 2/3 of length? When the string vibrates with 3 antinodes and 4 nodes. In which harmonics in vibrating string the wavelength is equal to 2/3 of L, the distance of the string? In the third harmonic. In where? In the third harmonic, wavelength is equal to 2/3 of its length. What about frequency? Look. Frequency equal to what? Fn NV over 2L. N is equal to what? N is equal to 3, third harmonic. N 3. V over 2L. Guys, V over 2L is not equal to F1? Yes. What is remain? F3. 3. F3, bring down this F3 and bring down this 3. And instead of V over 2L, is it possible to write down F1? Yes. F3 is equal to 3F1? Yes, of course. Okay? This is frequency of the third harmonic in a vibrating string, in a standing wave. Look, this is F3. Third harmonic consists of how many antinodes? 3 antinodes. How many nodes? 3 nodes. Number of nodes with number of antinodes is always equal? Yes. In a vibrating string, number of nodes determines the number of harmonics. Fourth harmonic, guys. In the fourth harmonics, according to its name, number of nodes 4. Antinode is equal to number of nodes 4. Number of nodes in vibrating string bigger than number of antinode by factor of 1. 5 nodes. In the fourth harmonics, vibrating string, how many antinodes do we have? 4. How many nodes do we have? 5. The figure will be like this. 4 antinodes, 1, 2, 3, 4. The standing wave, because it's fixed at both ends, the incident wave reflected by this end because it is fixed. Okay? These two ends are fixed. We have 4 antinodes, 1, 2, 3, 4. And 5 nodes, 1 node, 2, 3, 4, 5. Okay? 1, 2, 3, 4, 5 nodes. How can you determine wavelength? Guys, look, wavelength is equal to what? 2L over N. Fourth harmonic. Lambda 4 is equal to what? 2L over 4. Shortcut. Cancel to each other. The fourth wavelength is equal to L over 2. L over what? L over 2. What about L? If you rearrange, 2 times the fourth wavelength. In which harmonics wavelength is equal to half of its length of the string? In the fourth harmonic. Once again, listen carefully. In which harmonics wavelength is equal to half of its length? In the fourth harmonic, when the string vibrates with 4 antinodes and 5 nodes. Or another way, another question. When does the length of the string L is equal to twice of its wavelength? In the fourth harmonic, when string vibrates with 4 antinodes and 5 nodes. How can you determine frequency? Frequency for each harmonics, NV over 2L. Replace, instead of N, write down F4, 4 frequencies, 4V 2L. instead of this V over 2L, is it possible to write down, bring down this 4? What is remain? V over 2L. V over 2L is equal to F1, yes. And also according math basic, you can simplify F4. It's gonna be what? 2V over L. In which harmonics frequency is equal to 2V over L? In the fourth harmonic when the string vibrates with 4 antinodes and 5 notes. Guys, by increasing number of antinodes, what happens to the frequency? By increasing number of harmonics, frequency becomes increased and wavelength decreases. Okay? Guys, which figure is the simplest frequency or the fundamental frequency? Which one is the fundamental frequency? When the string vibrates with 1 antinode. Okay? F1, can we say instead of F1 lowest frequency? Yes. So what about lambda 1? Can we say this is longest wavelength? Yes. This wavelength is biggest. This is the biggest wavelength. As the number of harmonic increases, wavelength becomes decreased. By increasing number of harmonics, frequency also increases, but wavelength gets lower, decreases. Number of generated waves increases. Each loop corresponds to a half wave length. In a string, guys, in what? String, standing wave in a string. Minimum number of nodes is equal to what? 2 nodes. Do we have 1 node in the vibrating string for the standing wave? No. The minimum number of nodes, how many nodes? 2. This is minimum number. We don't have 1 node in a vibrating string. What about antinode? The minimum number of antinode is what? 1. Minimum number of nodes 1. Minimum number of antinode minimum number of node is 2, but minimum number of antinode is 1 antinode. In a string, the number of nodes is more than number of antinode by factor of 1. Number of nodes in vibrating string is equal to what? A plus 1. A plus what? A plus 1. In a vibrating string in a standing wave, number of antinode less than number of node by factor of 1. If you rearrange this equation, you will get this equation. Number of antinode is equal to number of node minus 1. In a vibrating string, the number of harmonics or number of harmonic is equal to number of antinode. In which type of standing wave, number of harmonics is equal to antinode in a vibrating string? In what? In a vibrating string, number of harmonics, what is N? Number of harmonics A, number of antinode. In a vibrating string, N always bigger than antinode by factor 1. A always less than number of node by factor of 1. In a vibrating string, both even harmonics and odd harmonics are present. As you can see here, how many harmonics do we have? 4. 1, 2, 3, 4. So this should be 4. Okay, we have many harmonics. You can calculate even for the 20th harmonics. Harmonic number 20, 25, 100, you can find it. Okay, we have a lot of harmonics. But guys, in a vibrating string, which harmonics are present? Odd harmonic like 1 and 3, or even harmonic both? In a vibrating string, both odd harmonics and even harmonics are present. What do you mean by odd harmonics? F1, F3, F5, F7, F9, and so on. And what about the even harmonics? We have F2, F4, F6, F8, and go on. Okay. The standing wave in a string has the longest wavelength and lowest frequency when the string vibrates with how many antinodes? One antinode and two nodes. When does, in a standing wave for the string, the string has the longest wavelength? When it vibrates with one antinode and two nodes. As you can see in this figure. This is the longest wavelength or lowest frequency. Longest wavelength, lambda 1, lowest frequency, f1. Frequency is inversely proportional to the wavelength because we are considering the greatest possible wavelength. The frequency is the lowest possible frequency of the standing wave on the string. Guys, look. If the string vibrates at one of these frequencies, the sound wave produced by the surrounding air will have the same frequency. Okay? At a given medium, at the same temperature, the frequency of the harmonics waves produced the standing wave or surrounding air will have the same frequency. However, the speed of this wave would be the speed of the sound wave in the air. Number 9. As the number of antinodes increases, when the number of antinodes increases, what happens to the wavelength? Decrease. At constant what? Strength, length. Okay? Because wavelength, also you can say 2L over A. At constant L, what is the relation between wavelength and antinode? Is directly proportional. More antinode, it means that more harmonics has less wavelength. The distance between two nodes is respectively is equal to half wavelength. Distance between what? Two nodes. Guys, look. This is sending wavelength and this is reflected because it is distance between two nodes, guys. From here to here, we have one wavelength. Okay, and from here to here, we have another wavelength. One wavelength and one wavelength. Guys, each circle corresponds to half wavelength. How many circles do we have here? Two circles. Two circles, it means that one wavelength. Distance between two nodes respectively, node and node. How many wavelengths do we have? Half wavelength. Half wavelength between two nodes. What about between three nodes? Distance between three nodes respectively. 1, 2, 3. Distance between three nodes. How many circles do we have? We have two circles. The distance between three nodes is equal to one wavelength? Yes. What about distance between two lengths? We have one circle. One circle corresponds to half wavelength. Distance between two nodes respectively equal to half wavelength. Distance between two antinodes respectively also is equal to half wavelength. How? Look. Distance between two antinodes respectively. A. Distance between two antinodes is equal to two half circle, okay? Which means that we have one circle here, half wavelength. Distance between two antinodes is also equal to half wavelength. The distance between node and adjacent antinodes. Node and adjacent antinode is equal to quarter. Distance between node and antinode, Distance between node and antinode respectively is equal to what? Quarter wavelength. Distance between node and antinode, quarter wavelength. Distance between two nodes, half wavelength. Distance between two antinodes, also half wavelength. But distance between three antinodes equal to one wavelength. Distance between two adjacent antinodes with the same phase difference, one wavelength. What is the same phase difference? Look at this figure. This is incident pulse or incident wave, And because this end is fixed, this wave will be reflected and inverted. Okay? Sorry, I have to draw a nice figure. Sorry. Okay. We have three antinodes here, but these two antinodes, we can say these two antinodes, they have the same phase difference. Okay, they have what? The same phase difference. But these two the two adjacent antinodes cannot be said they are in the same phase difference. These two yellow antinodes is also, we can say this is the same phase difference. So the distance between two antinodes with the same phase difference, is equal to one wavelength. Distance between two adjacent antinodes with the same phase difference equal to one wavelength. Distance between three nodes equal to one wavelength. Okay? Look at this question, question 3. The figures below show the stretched string vibrating in several of its nodes. If the length of the string is 2 meters, what is the wavelength of the wave on the string? But guys, look. In a string A, it must be integral number 1, 2, 3, 4, and 5. A can never be a decimal number, guys. This is wrong, be careful. A cannot be a decimal. It should be integral number 1, 2, 3, 4, and so on, okay? What is the wavelength of the wave on the string A, B, and D? A, B, C, and D, no problem, okay? For the figure A, guys, do we have L? Yes, 2 meters. Number of harmonic, 1. How did you know? By the figure. Because number of harmonic is equal to number of antinode. In a vibrating string, number of harmonic is equal to number of antinode. Number of harmonic, 1. Antinode, 1. Node, 2. Wavelength is equal to 2L over N. Wavelength for the longest wave, it becomes longest wavelength because it is first harmonic. 2 times, do we have L? Yes, 2. Number of harmonic, 1. Wavelength is equal to what? 4 meters. In the longest wavelength is equal to twice of L, yes. L, 2 meters. 2 times 2, 4. The answer is 4. When in the second harmonic, N is equal to what? 2. Antinode, 2. Number of nodes, 3. Wavelength, 2L over N. 2 times 2 over 2. 2 with 2 cancel. Lambda 2 is equal to L. When does wavelength is equal to L and is equal to 2 meters? When the string vibrates with 2 antinodes and 3 nodes. For third harmonic and fourth harmonic, you have to do the same procedure, okay? When does the longest wavelength is produced in a vibrated string? This is very good question, guys. Be careful. When does the longest wavelength, what do you mean by longest wavelength? Lambda 1. Lambda 1 is equal to what? 2L. In the longest wavelength, how many nodes do we have? 2. How many antinodes do we have? 1. When does the longest wave is produced in the vibrated string? It should be mentioned in the question about string or pipe. In a vibrating string, when the string vibrates with 1 antinode and 2 nodes, in this case, the object or the string has the longest wavelength. If the string vibrates 1 antinode 2 notes. As the number of harmonic increases, the frequency and number of vibration also increases. Look at this question. Find the wavelength lambda 5 and frequency F5 fifth harmonic for the next possible case in the harmonic series. Lambda 5 is equal to what, guys? Before writing lambda 5, lambda n is equal to 2L over n. Fn is equal to nv over 2L. Lambda for the fifth harmonic is equal to 2L over 5. And frequency for the fifth harmonic is equal to 5F1, or you can say lambda 5 is equal to N5 V over 2L. Both are correct. Be careful. You can say F5 is equal to 5F1 or 5V over 2L. Okay? Guys, that's all for today. We finished the standing wave on a vibrating string. Standing wave on a vibrating string, the two ends of the string must be known, fixed at both ends. Both ends must be known always. Okay? And the maximum point of the string, when it goes up or down, it becomes antinode. In a vibrating string, the shortest possible frequency is equal to V over 2L. And the longest wavelength, lambda 1, is equal to twice of length of the string. In a vibrating string, number of nodes bigger than number of antinodes by factor of 1. For example, if you have 2 antinodes, it means that how many nodes do we have? 3 nodes. In a vibrating string, number of antinodes determines the harmonics. For example, if number of antinodes is equal to 3, it means that this harmonic is the third harmonic. A number of antinodes is equal to n small number of harmonics. Thank you for listening. Keep up your best doing. Inshallah, in the next lesson, we will explain standing wave in an air column and in the pipe.